Okay, let's begin Module 3 with our first lecture. Sort of a reset on linear programming. We've sort of built our way into the topic by thinking about sort of available information and what kind of trade-offs could we think about, and how might we construct sort of a mathematical representation of those sort of decision contexts, right? These nexuses or nexi or whatever the plural of that would be for decisions. And so we should step back and think about linear programming as it's developed as a topic, and you'll have some readings this week that will take you through that a little bit more clearly to try to get an idea of how people speak about this in an academic context, so that as you encounter it, you'll understand sort of the full scope of this, not just as a technique that we've sort of worked our way through in an ad hoc formation. So there are ways to classify linear programming problem types. The first would be maximization versus minimization, and we've seen one of each of these. Maximization typically requires some upper limits, right, because you're trying to make a function large, and so you need upper boundaries to close off the options, and then you're choosing in that sort of direction of the upper boundary. It's common to have some kind of maximizing returns or a metric, whatever the metric might be, subject to resource limits. For minimization, it goes the other way. So the problem is to find a small value, a small objective value, and so we're trying to, the problem tends to push itself towards zeroing out the objective, and so there usually has to be some lower limits, some requirements that are set, right? So simple enough, you're going to plan your meal budget for the week, make it as small as possible. Well, don't eat. Well, that's not okay, and so we need some lower limits on how much must be purchased, and then once you've set those lower limits, you fill it around that, and so we're sort of working around the lower end of the boundary. So two different problems, two different sort of pictures when we graph those things in problems that only have two choices. Again, could be some related metric, and so when I put these ideas or this notion of metric, I want to keep in mind these objective equations don't have to be purely economic measures. They could be things more like anything that could be an objective in some context. So to think about it, I looked up a few. So it could be sort of an output-based metric, trying to sort of design a production line and understand the throughput. Could be a sales target. Could be some kind of distance measure. If you were thinking about quality control sort of model, it could be some kind of error rate, trying to make it as small as possible while thinking about moving things along as fast as possible or meeting some targets on throughput. Customer satisfaction. So, a big piece of the modern data world is reviews. And people collecting information on customer satisfaction, customer feedback, and so that could be important. These will all be sort of problems that sort of lend themselves to a metric where there may be decision points that could have influence over those. So they're not classic economic problems, but they would have the same sort of approach. The classes of problems would, if we were to think about moving away from sort of the direction, but to the class of problems, it would be resource allocation versus blending and mix type problems. So resource allocation, you have some things, you want to convert those into things that you actually market or sell. Blending or mix problems, you have some things, you want to blend or mix those different things together, subject to some requirements. Those are this is sort of the production or crop problem. This is sort of the diet or construction of a diet problem. Network models are a little different, and that's going to be in the second half of this module. We'll go through those in detail, looking at transportation, but they tend to focus on nodes and sort of a set of choices that have sort of two linkage points that we could think of as being nodes, and which nodes do you want to connect. And of course that the classic is the transport nodes between source and destination. You have many options. How do you get things moved around to meet the requirements at the lowest cost? And then the last sort of class is games. We'll leave that for later, and we probably won't even use a linear programming approach to that. Linear programming is not the most efficient way to solve sort of games, competition games, where you're thinking about strategy. Just to look at our examples of each, the resource allocation problem, production of 2 items. So this is a model that has 2 types. So there's 2 goods. There's standard bags here, deluxe bags here, a feasible region that's sort of cordoned off by different constraints. And so these are returns to the decision maker. We have sort of these physical constraints that say you can't exceed this, even though you have enough other resources to make larger amounts. When you consider all the constraints simultaneously, you have to be down here. It's a classic problem for firm output supply choice, but anything else, right? Anything else where you're trying to drive to a maximum, you set some upper bounds. You could set other boundaries as well. And maybe we'll talk about some of those. But there could be some constraints on I don't want to let the sales of this number exceed a certain amount for some sort of internal consideration. Maybe there's a transportation or a constraint in warehouse storage that says, or even just the market demand says that, okay, we can sell a certain number of premium or deluxe bags, but that market isn't mature yet, and so we're going to max out at this much to keep from having too much inventory. And so you think about sort of an internal policy constraint that isn't quite the physical limitation. Sorry about this scan. It's that crispy and crunchy problem. So mixing 2 types of cereal together to make a breakfast meal. And this is the minimization problem, or the blend. I'm going to blend my 2 cereals together into the same bowl to meet at the lowest cost what I consider to be the requirements of a breakfast. And so we're mixing those 2 things together. We're trying to drive the cost low. This is the cost line. The Krispies axis is here, the Crunchies is here, and this constraint can move this cost line can move in this direction or out this direction. We're trying to make it low, and so we're driving it down to this corner point eventually. There are all kinds of sort of policy constraints that might be interesting to think about in kind of a blend problem. For example, 2 that show up recently in the sort of policy world on energy and utility provision. So we've had renewable fuels mandates for quite a few years now, and as a utility or an energy producer is coming together with sort of feedstocks for producing maybe electricity. They have to decide what they're going to purchase and what kind of mix they're going to do. And if there's a policy that says 20% of your output needs to be based on renewable resources, then that's a hard policy constraint that enters into this that may not actually match up to any physical limitation of the firm. The other one here would be maybe a maximum emissions output. So you can go at lowest cost, but you have to keep track of your emissions, and if you have a high emission, it's typical to have low cost resources that have high emission content, and so you may be upper bound limited there on your blend for utility generation. I'm not going to talk too much about the network problem because we have several lectures on it later, but A, B, and C here are the sources. You can see they're sort of spread out on the coast here as ports, and then there are these destination factories for this firm at 1, 2, 3, and 4. And so I think the way this problem is going to be described is there's these motors that are shipped here into Europe, and then those motors have to be moved to assembly plants where they're going to actually make cars. And it's something of a hybrid type problem. So you see these numbers here, and the numbers here say that 500 motors are going to arrive in Amsterdam, 700 in Antwerp. At the assembly plant in Liège, they're going to require 200 motors, and over in Nancy, they're going to require 900. So you have these sort of resource limits. This is the most you'll have from any of the network sources, and then you have requirements, minimums that must be met over at the destinations. And so the typical way of doing that problem is to minimize the cost of meeting all these targets. There's some special mathematics in play there that we'll talk about later, but basically if these are all minimum requirements, then you better have enough motors arriving in the different ports, and so you have to think about how that would work. And then there's a related problem. Think about these 4 plants, and maybe you have a vice president, I think in the reading, that's assigned to visit one and do an audit or conduct an audit. And how do you assign those 4 people with different skills to these 4 different plants to go out and do their audit? Or think about the basketball player problem. You have LeBron James on your team, and he can only play one position, but you have 5 positions to fill, and he may be the best at several of those. How do you assign your players out to those different positions? Okay, moving on into our classifications here, we have different constraint types. I've already talked about this a little bit. You have sort of the structural constraints that might be considered physical or sort of measurable things. And so you have physical limits on available resources, or physical requirements on how you're going to contribute to the mix of products, physical requirements on shipments. You have a certain number that can arrive or that must arrive, and a certain number that is the most that can depart from a specific node. So we would tend to think of those as structural. They sort of set up the basic, what we call the economic sort of structure of the problem. So in these problems, we're going to be measuring some economic objective. Those constraints are really going to work for us and help us come up with sort of economic rankings or economic interpretations of the solution. Why did we choose option A over option B? Those kind of things. The second set are what we might call policy. And so we talked, I already mentioned a little bit the utility generation. The idea that there could be regulations that come from outside the firm that limit activities or put thresholds that make either for upper or lower bounds. You have to use this much renewable. You can't use things that emit more than this, those kind of things. But there could be internal sort of policy like constraints in the problem. So it's important to keep in mind, and maybe there's a better term for this, but I typically just call them policy constraints. It's an internal policy. We are abstracting a problem. Almost all of these, when you put them in context, they're a small piece of a much bigger business strategy, business planning situation. So we're thinking about a small department with 2 products and some limits on a few production lines that are set up. That has to fit into a bigger firm plan that has to deal with demand for the products and think about how we're going to market these things and all sorts of other related things. And so when we abstract or sort of single out or hollow out this small piece of the problem we have, it's possible that only the physical or structure constraints that we measure may not be the only thing we have to think about. We may have to think about some internal policies that have to be maintained. Or if you were thinking about purchases in the household, some kind of household structure. So an internal policy there may be some kind of cultural thing where a family is budgeting to eat at the lowest cost, and that gives you the structure because you sort of know what the prices are and what the nutrition content is, but they have a policy of one family meal outside the home every month or every 2 months. And so we would want to account for the nutrition that they get outside the home, right? So that we're not double counting. And so that would be sort of a policy constraint that exists there. Same thing may happen for firms. To keep 2 other departments employed or running, we may maintain some production lines that are not most profitable internally or in that sort of abstracted version of the problem, but we're going to keep producing because there's some other reason in the firm, and we may not get the pure economic optimum for our division or our department. Then some other economic constraints. Typically those pop up in some dual or competing objective problems. We won't hit those very much. Constraint and the economics of constraints are really the hallmark of LP analysis. So it's the place we go to measure things. So a policy constraint you would see as the sort of classic. If a firm is going to adhere to the regulatory structure, what is the cost? And so if we took that constraint away, how much can they lower cost? And so the difference in those two costs is clearly the cost of that firm, how much they're sort of being implicitly taxed through this regulatory structure. So they may not be taxed explicitly at all. There may not be any tax rate attached to this, but having to deal with a regulation that increases your cost is like a implicit tax. Some internal policy may have a tax or a cost or a marginal cost attached to it. If a firm has a market share or penetration constraint that says we're going to keep pumping this product out as we try to develop this market for this new specialty product, there's already an advertising and a sort of a sales rep coverage strategy going on somewhere else, and while internally to our division it looks like it's a part of it's not the best approach, that internal policy makes us produce, and so we can measure part of the cost of this overall strategy. How much is that sort of taxation that's coming from outside our department, outside our decision context, but it is still in the firm. And then of course structural constraints, what's the value of additional resource? So the classic is, I want another acre of land, how much can I pay for it? Well, you add to the problem that 1 acre and see how much value it contributes. So resource Y at a level of Z. Structural constraints again, what is the value if we were thinking about a diet? We need zinc, we need calcium, we need all these things. Well, what if I just took a multivitamin and swapped that in for trying to get those from my food? How much would that multivitamin be worth, and is it cheaper to just get it that way? And then in the remainder of this module, we're mostly going to be focused on constraint economics, really in terms of sensitivity. Okay, and so our last sort of piece of this, again, sort of a reset lecture, or maybe you want to think of it as big picture, is what are the assumptions? So when economists or a textbook author sits down and says there's some limiting assumptions to linear programming as a topic, you start from the idea these are abstractions. We're trying to deal with a world of complex interactions and get that and behaviors and try to put together a math model for it. Well, that imposes some limits on its own, and then doing this linear programming approach has some of its own sort of specifics. And these are the four that are most commonly cited: proportionality, additivity, divisibility, and certainty. So first, proportionality. And this just means that the level of activity is irrelevant to the contribution to the objective function or the unit's change in a constraint inequality. Simply put, these coefficients in the model are going to be constants. If the first acre earns me $50 of gross margin, the 50th acre is also earning me $50 of gross margin. So that's proportionality. Doesn't matter how you scale things up or down, you're getting the same returns. And if it also requires producing an acre of land, an acre of corn requires 3 hours of labor, then the 50th acre requires that same 3 hours, right? So there's no sort of increasing returns to scale, decreasing returns to scale, that kind of thing. So what are the implications? Well, the most common one is that marginal diminishment that you think of in sort of classic microeconomics is not present. So no marginal productivity loss, no marginal utility diminishing in these. And so those are, that they may occur locally, but they're not there in these linear functions. There is a compensating factor, and that is in the feasible space. Because, we've talked about this a little bit, every region or neighborhood of the boundary of the feasible space is going to be governed by a different constraint. That means that as you move around the corners of the constraint, of the feasible space, those trade-offs are going to change. And so you get something that could look like a normal supply function, like a normal demand function out of these. And so that's something we won't talk about too much, but it is the sort of factor that accounts for all this, is that feasible space approximating what would look like a true economic constraint that's curved allows us to get a pretty decent linear approximation to the economic decision making. And of course there is the fact that people in real world decisions have to make lumpy decisions anyway, and so they tend to adopt proportionality as an assumption, whether it works or not. The second one is additivity, and basically says contribution from one activity doesn't directly influence the return or contribution of some other activity. And that goes the same for constraints. So if I decide to produce 5 acres of corn, or 5 acres, I think a classic example is 5 acres of soybean, there's no productivity gain or lost or impact on what happens on the 6th acre if I decide to produce oats or something on it. So in short, you can sum up all the linear components and the total is just going to be the total. There's no interaction, no multiplication between activities that could happen. And that is the implication. No explicit interactions, even though they may happen in the economic setting and in the real world. We're going to have to abstract away from those. Sometimes we might try to bring them back, coming up with like crop rotation activity definitions that allow for these interactions. And so there are workarounds to get around almost any of this, but it's an advanced topic, so it's the kind of thing we might talk about when you come here for residency. And then of course the compensating factor here is also that there are interactions that make their way through the feasible space, through the constraints. You had an example of this in Module 2 where you added a unit of land to the right hand side of your constraint in the cropping problem, the 3 crop problem. And so what happened was when you added that acre of land, now there's an interaction between, I believe it was oats and corn production, because what you actually do when you add that acre of land is you pull back on production of corn to release up some labor to be able to expand the oats production in the problem. And so that's an interaction, but it actually works through a second constraint. So the first constraint, the constraint that's directly changing, isn't the one controlling the interaction, but the other one is. We have some other sort of assumptions here. Divisibility, basically you must allow, and this is really the algorithm's fault, you must allow partial activities. Basically, if it says produce 2/3 of an airplane, that's your part of your production plan. Is it serious or is it not too serious? Well, in serious cases, you go to integer programming, which is a adaptation or iteration on linear programming that allows for solving with the requirement of whole number activities where it's required. That's also a recitation residency topic that we'll do. It comes at a cost. All that economic analysis we're going to learn about in this module gets wrecked. So we don't get our normal sensitivity results. The only option is to go in there and do a ton of scenarios and try to generate sort of sensitivity through those, and not get the sort of classic analysis, sensitivity-based analysis that we're going to talk about. Then the second one is certainty, and this is a topic we're going to move into in Module 4, is uncertainty. We assume the coefficients are known. There's no uncertainty, no analysis of decision making under risk. Even when there's decision makers risk neutral, we want to know what their facings are, what the uncertainties are. Is it serious? Is it not so serious? Well, there's stochastic programming is the iteration that allows us to think about randomly drawn parameters, right? So if you know the distribution of coefficients and you think there's some problem that may cause the firm to not know sort of what rate of transfer you're getting or rate of conversion you're getting with certainty, then you can account for that. Certainly important in a lot of like animal feeding problems where you know that you're not going to get perfect quality and perfect delivery to every animal, so it's typical to put in a random draw there and get some distribution to think about those and think about the risk and sort of how much sort of insurance feed do you supply? And then of course risk programming is a huge topic that we're going to deal with in this class as well. It requires a nonlinear objective. There's no way to get around it. If you want to measure variance, measure the variability of returns, you need something that is squared, and that's not linear. So with that, I think I'm going to close out this. And I hope as you've read through this, you've seen some of these things pop up in our readings already. And so maybe me talking through it in this sort of one-shot, again, thinking about classification of problems, thinking about the constraints and their classifications, and then thinking about these assumptions, gives us sort of a base level of thinking about sort of big picture how we might talk about this technique, especially since after this module we'll be jumping into some other techniques for simulation that will have their own sort of set of limitations we'll have to think about. So that'll be something we can contrast. With that, I'll sign off, and you'll have a quiz that you should be doing right after this.